All right, everyone. How are we doing today? Good, bad? Okay. All right. We are marching ever forward in our material here. We of course um, just took an exam. I will try to get those back as quickly as I can. There's just it's a process. So give me a little bit of time to work through those. And what we'll do in the meantime is continue on with the stuff for this course. We have two chapters remaining. Okay. Chapter 15, which is next for us, has to do with integration in higher dimensional contexts. Okay. And then chapter 16 is where we um, put a lot of ideas together, combining um, all of the ideas of differentiation and integration and all that stuff for this class. But in order to do that, we have to develop some skills and some understanding before we move on. All right. So to start off with, we need to recall Riemann sums. If we have some kind of curve that looks like this, all right, if I wanted to compute what we call the definite integral, what we do is we select some range of values from A to B. So this would be what we call the definite integral from A to B. And then an approximation to this would be represented by a series of rectangles that we use to approximate the area under the curve here. Okay. So the idea is that we manipulate this situation here, and we're trying to come up with this value. Okay, well there's maybe it makes more sense if we put the star up here. Whatever. Okay. So just as a reminder to everybody, there are some things going on with when we set up the Riemann sum, and there are multiple ways to actually make it work. All these definitions are equivalent. Okay. Probably the standard way that you were taught how to do this is that you have the interval from A to B, you divide it up into n equal width intervals, and then you increase the value n, and each time you do that, you just end up with an entirely new set of rectangles where they keep getting thinner and thinner and thinner, right? Okay. Now, there are other ways to do this, okay? Another scheme would involve taking the rectangles that already exist and then deciding that you were cutting them in half or somehow, and then doubling the number of rectangles so that if you've already selected partition points, that you don't have to reselect the partition points. Because if you just increase n by 1 each time and change all of those interval widths and keep shrinking it that way, you actually have to pick a completely new set of points every single time you compute the an approximation to the integral, which can be an issue. The other thing that can happen is that, and the reason that I drew a star here is that there's nothing that says that there has to be a system at which point I select for the height of the rectangle. So the standard Riemann sums that you did back in Calculus 1 were either left sums or right sums, where you pick the left endpoint or the right endpoint, okay? Or maybe you pick the midpoint of the interval, okay? It turns out that that doesn't matter, okay? For every rectangle, I can select any point I want in that interval, and if the theorem works correctly, as the width of the rectangles goes to 0, I eventually pick all of the points anyway, right? So they can be randomly selected, all right? So in the definition of a Riemann sum that's used by the textbook, this actually means a randomly chosen sample point in each of the subintervals, okay? That matters because there are numerical approximations that this allows that we wouldn't necessarily think of as being something that we could do. Okay, I'll talk a little bit about that later, but keep that in mind. So there's kind of three ways that we can define how Riemann integrals work. Okay, and if you take a class called Advanced Calculus, you'll talk about these in more detail. You should take calculus or advanced calculus. It's fun. It's calculus, except you prove all the theorems. All right. Anyway, so we have discussed here a little bit what's going on with definite integrals to remind ourselves of how this works. Okay. We want to instead do this in a situation where we're talking about integrals in the context of 3 dimensions. Okay. Now, I say 3 dimensions. We have to be careful about this. All right. What I really mean is instead of the area under a curve, we're going to be talking about the volume under a surface. Okay. So we have some surface. It's not the easiest thing in the world to draw. All right. And below it, what we're interested in is some rectangular region. Okay, here we have a point A, here we have a point B, here we have a point C, and here we have a point D. Okay. And what's going to happen is that when I compute the value of the integral, I'm going to get that volume. Okay. So the geometric idea here is that we're talking about the volume under a surface. All right. So does that make sense? Okay. So got a couple pictures that I want to show. One, I'll do a quick sketch, and then we'll show some computer versions of this. All right. So if we're talking about integrating over a rectangle, all right, what we're going to end up with instead of a list of partition points is a grid. Okay. And on this grid, I mentioned before that we're allowed to choose any points in each of the subintervals for a one-dimensional integral, which means that I can choose any points in one of these grid spots for evaluating a double integral. Okay, so if I select these points at random, all right, the height is going to be the height of the surface at some randomly selected points in each of those tiny rectangles. Okay, and if I have some surface and I am trying to approximate the area under, oh, oops, sorry, there we go. Area under the curve here. All right, we see what's going on here. All right, this is an 8x8 grid, and we can see these elements here. All right, this is a 16x16 grid, and we see that our rectangles are smaller. All right, and we see that we get better and better approximations as we increase the number of points. Okay, so it works the way that we want it to. All right, now we write out the definition of what a double integral looks like. It looks like this. So when I say a double integral, the way that we write this is we literally just write two integral symbols next to each other. And the set over which we are integrating is going to be underneath the double integral sign. It's not a subscript, it's written underneath. I have some function of two variables that I am integrating. And what we are going to say is I'm integrating over dA. Okay? dA is one of these area elements. All right. And like the Riemann sum, we have to define this in terms of a limit. This is actually a limit in two variables. We have both m and n going to infinity. And we are going to have a double sum. We have I equals 1 to m, and j equals 1 to n. I's basically are the rows, and j's are the columns. That's how you can think of them in the grid. And so we have the ijth sample point for x and for y, being where we evaluate the function. And delta A is the area of one of these little grid squares. Make sense? So the book for this definition is assuming that the area of all the little delta A's is the same. All right. That does not necessarily have to be true. Okay. All we need is to set up our limit in a way so that the area for all of those things eventually goes to 0. Okay. They don't have to go to 0 at the same rate. The delta A's don't always have to all be the same size. You could write an equivalent definition of this with delta A ij, where it does weird stuff. But as long as the area goes to 0 for every single one of them, the definition will work. All right. So this is our Riemann sum version of this. This is the one that corresponds to, of course, the numerical computed version that we saw before. Okay. Computers can't compute this. All right. They use this as an approximation. Okay. The larger that M and N are, the better approximation we get to the value of the volume under the surface, or just the value of the definite integral, because they're all definite integrals. All right. Because I'm more interested in doing analytical examples, I'm just going to mention these things, but they are important. Okay. Number one, we can do numerical approximations. It works the way that you expect it to work, right? If I have a simple grid, and we'll just choose a 2x3 here, okay? We select a point in each one of these regions, okay? And the way that I would approximate the area under the surface on this grid is to just take each of these heights, okay? So there's a height associated with that choice of point, right? So this would be f of x11 star, y11 star, because this is 1, 2, and this is 1, 2, 3. And then the row index is before the column index, right? So I equals j equals. I'll write this up here so it's a little bit more clear. So the i's are on the row, the j's are on the columns. Okay, so I have a height from this. This would be my delta A. And then I add all of these up. So in this case, I would have 6 values to add up, and that gives me my numerical approximation. Questions about that? All right. Okay. Okay. I'm sure that you were also told in your Calculus 1 classes that the midpoint rule is a really good way to do numerical approximations for integrals. Okay. It still works here. Okay. Now, for a midpoint, okay, it's the midpoint, of course, is the center of the rectangle. But in order for us to say center of the rectangle in a way that's consistent, it's the centroid of the shape, right? If we imagine that the rectangle was a thin plate, it's the center of mass. You should have talked about lamina in Calc 2. Yes. Okay. Maybe we'll talk about those later too. Anyway. All right. So a couple of approximation schemes that work the way that you would expect them to. No surprises. Okay. Now, the meat of the section has to do with this. iterated integrals. Okay. Okay. Having to do the Riemann sum and take the limit in order to evaluate double integrals stinks. Okay. We don't want to have to do that. All right. We didn't like doing it in Calc 1, I'm sure. All right. It got annoying really fast. And so then we introduced the fundamental theorem of calculus and the idea of antiderivatives. And eventually everybody was happy for about 4 weeks. And then everybody forgot how to integrate between then and coming to this class. And now we get to relearn how to integrate it. All right. So here we go. If we have a expression set up so that it looks like this. Okay. This is the picture that has been going on in the background for us for the lecture so far. Okay, so there's some rectangle. Down here in the XY plane. And then up here on the Z axis, we have some surface. And what we want to do is we want to find the volume under here. Okay, so we're out to find this volume. Make sense? So this is what we have set up, and when we write our integral expression, all right, the thing called an iterated integral is one that is written in this form. Okay, this is what makes it iterated. The fact that instead of a dA there, talking about the area element over which I'm integrating, we're looking at individual variables. Okay. This is interpreted like this. Okay. And the reason that we refer to it as an iterated integral is that we compute the first integral first and then the second one. All right. So much like we only differentiate with respect to one variable at a time, we're also going to be integrating with respect to one variable at a time. So let's do a couple of examples. All right. So eventually, you will probably get to the point where you don't need to write it this way. But when you are adjusting to this, it is my recommendation that you be very careful with the parentheses until you feel pretty confident that you're looking at things and not making mistakes. Okay? Very easy to make omissions and writing mistakes and things like these because I'll tell you right now, over the course of the chapter, we're only going to get more and more sophisticated looking things like this. All right. So it's very easy to make copy errors. It's very easy to make interpretation errors. So be careful. Use a lot of paper if you need to use a lot of paper. Okay. Um, don't don't make silly mistakes by trying to write things in too condensed of a format. All right. So what we do is we do the interior problem first. Okay. The interior is a definite integral with respect to y. Okay. So what we do is we integrate with respect to y here. All right. The integral of y is 1/2 y squared. The x is a constant, so it just goes along for the ride. And then we evaluate the definite integral for the values of y. So everything that's not y is a constant. I just moved it out front. And then it's the first value plugged in minus the second value plugged in. Right? Okay. So what this gives us is the integral from 0 to 3, 3x squared over 2 dx. Then we do the next definite integral. The integral of x squared is x cubed over 3. We evaluate it. Plug in 0, we get 27 there. And then plug in 0 and get nothing, so this is going to be 27 halves. Make sense? Seems okay? All right. Okay, now, the next thing that we want to do for this example is do it the other way. So I have switched both the limits of integration and the order of integration. What I've done is switch the order of integration, okay? But the limits and the dx and dy have both switched. Okay, so now we write it as an iterated integral. Using our grouping symbols to keep things organized. X cubed over 3 So we get this, all right? So what we're going to get here is we plug in 3, we're going to get 27 over 3, which is 9. So we're going to get the integral from 1 to 2 of 9y dy. If I plug in 3, I get 9. If I plug in 0, I get 0. And we integrate this, which is really easy. 9 halves y squared, evaluated from y equals 1 to y equals 2. 9 halves times 2 squared minus 1 squared equals 27 halves. Okay. It is a theorem. We're very happy about this. But you can integrate rectangles in either order. Okay. So it doesn't matter if you do dx dy or dy dx. All right. You can look at the integrand, figure out which way looks easier, and then do that one first. Okay. In this particular problem, maybe doing it the second way was easier than the first way. Now, it's a polynomial, so it really doesn't matter, right? But that is one of the things that you should be looking to develop a skill for. Okay. Is examining the integrand and figuring out which variable do I want to integrate with respect to first. Because sometimes integrating with respect to one variable as opposed to the other is going to make things messy. Yes. If we do triple integrals, which we'll get there, yes, if you are doing a triple integral on a cube, then you would be able, or sorry, a rectangular prism, you would be able to integrate in any order you like. All right. In fact, this theorem that I mentioned has a name. Okay, it's called Fubini's theorem. And it says if f is continuous on the rectangle, r equals a set of all xy such that the bar, I guess. X is in the closed interval from A to B, and y is in the closed interval from C to D. Then we can switch the order of integration. Okay. So I will be mentioning Fubini's theorem a lot because it turns out to be really important. Okay. Now, Fubini's theorem technically has to do with rectangles, but it has extensions that count in other cases. I will talk about those when they are relevant. Okay. Seems fine. Okay. All right. More examples. One of the standard ways to define a rectangle is like this, as a Cartesian product of closed intervals. Okay, and the order matters. This is x and this is y. Okay, the variables are always in alphabetical order. Okay, we have to remember that. All right, so we're looking at this, and we have to set up our integral. Okay, we're told the domain, and we're told the function that we want to integrate. And we have two choices here. I can write this, or I can write this. This is a rectangle. Yeah, I mean, it's because it's the Cartesian product of two intervals. So we have 0 to pi and 1 to 2. It's a rectangle. Yes. So okay. It's hard for me to distinguish between these symbols. If it's typewritten, it's very clearly it's a different looking X than the one that you see for a cross product. It's thinner and a little bit bigger. Well, it might actually be the symbol for the cross product. I don't want to be wrong about that. It's contextually, it's shouldn't be ambiguous. Yes, that was a copy error. Thank you. dx dy over here. Okay. Looking at this side, how do I integrate that? Integrating with respect to y, right? How would I integrate this? With respect to y? This I have to integrate by parts. Yeah. We have to use the integral. This one will require integration by parts. Okay. That's why I'm doing this one. U equals xy, du equals y dx. All right. The one on the right is the U substitution problem that was suggested by the audience. Okay. It is much easier. Okay. So we do our integral here. Now, I am a little bit of a stickler for this because in the future it is going to make our lives much, much, much easier to the point of almost being necessary. Whenever I do U substitution, I always change the limits of integration. Okay? There are some folks who ignore the limits of integration until the end of the problem, go back to the original variables, and then plug all the numbers in at the end. I think that's a waste of time. Okay? So, when xy, sorry, when x is equal to 1, u is going to be equal to y. Okay? And when x is equal to 2, we have 2y here. I'm plugging in 1 and 2, replacing x. So it's okay to have variables in the limits of integration because we've seen this kind of thing when we talked about the fundamental theorem of calculus back in our previous calculus courses. And then we have sine u du and then dy. Part of the reason why I say parentheses are important so we don't get mixed up on stuff. Okay. So now we have the integral from 0 to pi of negative cosine 2y plus cosine y, is the antiderivative of sine is negative sine, and then we plug in the value of 2y, and then it's minus the other one, so we get 2 minus signs, which is why it's plus. dy here. Okay, I guess I technically skipped a step. People are like, oh no, he just plugged it in. All right. So the antiderivative, u equals y, u equals 2y. All right. Now we're ready to integrate again. The first one's technically a u substitution integral, but it's the easiest kind. Okay. All right. So here's the trick, right? Sine of pi, sine of 2 pi, sine of 3 pi, sine of 0, sine of negative 1 pi, sine of negative 2 pi. For every integer k, sine of k pi is 0. This integral is 0. Now, you would have gotten this if you had plugged in the values directly, but sine of 2 pi is 0 and sine of pi is 0, which is why it's... Okay, all right. And then because I will sometimes use them without thinking about them very much, I'll go ahead and make note of this. Those of you who've taken logic classes should already know this, but this symbol, this upside down A, is known as the universal quantifier. Okay. It is used as a stand-in sometimes for the English phrases for all, for each, every. Okay. And there's another symbol, backwards E. It's known as the existential quantifier. All right. Okay. It means that there is one thing for which this is true. All right. Both are equally important in math. Okay. So the existential quantifier shows up in things like the intermediate value theorem. If I have a curve where I know that one point is greater than 0 on the function and the other point is less than 0 on the function, all right, by the intermediate value theorem, there exists at least one point where the value of the function is equal to 0. If we have a continuous function here, right? If I draw a different curve, there might be more than one point where it crosses the x-axis, but there is at least one. Okay, that's what we mean by an existential quantifier. Okay, there's minimum of one case where the condition holds. All righty, so how are we feeling? Huh? Yeah, I know. We have to. Let's. I wasn't kidding when I was teasing people about the integration stuff. All right, we're gonna have to remember everything. Okay. um. All right. So there is a trick that I will be using a lot in class, but we have to be sure that we are using it only when it's appropriate. It's the kind of thing that looks really nice, and when it is available to us, is fantastic. But it makes people who aren't paying attention make mistakes, so it's kind of dangerous. All right, it's like L'Hopital's rule. You know, L'Hopital's rule is super powerful, but it only works some of the time, right? And you have to be good at identifying when it's okay to use it, because when you can, you solve the problem immediately. But if you can't use it and you do, you're very, very wrong. So separability has to do with the way that integrals are constructed. Okay, if I'm integrating over a rectangle and I have a integrand, but it happens to be the case that my integrand can be written as a product, and in that product, my each of my variables are isolated. Okay, so I can write it as a function that depends only on x times a function that depends only on h. Okay, if I can do this, then if I have an iterated integral, then what I'm allowed to do is write this integral as a product of the single integrals. Okay, this property where my function can be written as a product of functions that depend only on one independent variable is known as separability. Okay, if I have a separable integrand, then my product becomes a individual item. Okay, so I have one fewer minute than I would have liked. Okay, so we had this example before, right? We got the variables in the right order. Yeah, okay. This should be equal to this. All right, so we have x cubed over 3 evaluated from 0 to 3 times y squared over 2 evaluated from 1 to 2. This is 27, and this, sorry, this is, I didn't mess this up, did I? No, okay, sorry, no, this is 9. That one's 9, and the other one's 3/2. Sorry, I was going too fast. Okay, it's 27 halves. So all 3 ways we get the same answer for this problem. Okay, so practice. All right, do problems, get back into the swing of integrating. All right, because we will be doing a lot of trigonometric integrals. All right, we're going to introduce eventually coordinate changes and things like that, and it's going to become a fact of life. So mentally prepare yourselves and get used to writing everything out carefully so you don't make mistakes. All right, I'll see you next time.